How's it going, guys? Back at you with lecture video number 4 here. This is actually going to be the last lecture video for this chapter, so closing the books on this one pretty quickly here as well. So we're going to focus on today. I know we've been talking about the elements on the periodic table. We've not really stopped too much to talk about the periodic table itself, and that's going to kind of be what we do and focus on today. Starting with this kind of crazy-looking man here in the top right-hand corner of the page here. His name is Dmitri Mendeleev. And in the late 1800s, he arranged the elements, that were kind of known at that time, right? There wasn't a whole lot of them known at that time in the late 1800s, but the ones that were known at that time, he arranged them based on their physical and chemical properties. And honestly, that's not really a bad way to go about it, right? Arranged them by their physical and chemical properties. So he kind of did that in a way that he kind of grouped them together based on those physical and chemical properties. And comes to find out that actually wasn't that bad of a choice, right? He found that the properties repeated in a regular and periodic fashion, and that's kind of where that name periodic comes from in the periodic table. He was also smart enough to leave empty spaces on his kind of, basically constructed periodic table here because he knew that there were going to be elements that were not yet discovered. He knew that the more he was able to kind of put together this table, he was able to essentially predict that there were going to be holes in this table and that those holes were going to be filled with, newer elements that were going to be discovered, as time progressed. Now, the modern periodic table, which is the one that you guys work out of and have been looking at pretty much every single day, is based on his work, is based on Mendeleev's work. The change here is that all the elements on the periodic table these days are not arranged by their physical and chemical properties. They're actually, as you kind of came to find out recently, are arranged based on in order of increasing atomic number, right? In the increasing of that number of protons of that particular atom. Now, the makeup of the periodic table is essentially, it's grouped up into two different sections, right? The vertical columns that go up and down and the horizontal pieces that go left and right here. Now those columns are known as the groups or family, right? More often than not, they're going to be referenced as the group, and very, very rarely you at least hear me call it a family, but the groups are going to be the columns that go up and down, right? The vertical columns there on the periodic table. They have the same number of what are known as valence electrons, and we'll dig into more of what that means next chapter. And because of that, they actually do have similar chemical and physical properties. So again, Mendeleev's work was not all for nothing, right? He actually did a really good job of constructing his initial periodic table because he wasn't entirely wrong for doing what he did. Now, up next are our periods here, and these are the horizontal pieces, right? The ones that go across the periodic table from left to right. They are our rows that go across our periodic table, and each new row corresponds to the filling of a new principal energy level. And again, a lot of this, the verbiage here, valence electrons and principal energy level, those are going to be very useful terms that we use going forward into our next chapter, chapter 4 after this. Or, chapter 4. Oh, there we go. So, looking on now to this right here, of course, is the periodic table. It's pretty much exactly the same periodic table that you guys have been looking at recently. The only difference is the elements' name are not written in on this periodic table. So again, everything else is pretty much the exact same from what you guys are used to. The only difference again is that the periodic tables this periodic table doesn't have the elements written into it. Now, what I want to focus on for a brief minute here is actually this portion of our periodic table. Okay, it's the one that I'm outlining very poorly, but outlining on the periodic table here in orange. Okay, this partition here, right, that kind of separates, right, and if you guys look at your periodic table, you guys can all kind of see, and I'll even remove this orange line here. You can kind of see the bolded black line that separates. It's a very jagged line here that separates this section kind of from what's on the left-hand side of the periodic table and the right-hand side of the periodic table. So again, I'm going to outline it in orange here one more time for you guys, just so you can kind of very clearly see what I'm referencing here. Right, this section right here. Okay, this is called what's known as the periodic table staircase. Okay, it's the periodic table staircase, and this staircase is very, very important because it does a really good job of doing something really, really important. It separates our periodic table based on what's on the left-hand side, which is our metals. So pretty much everything on the left-hand side of this staircase here is our metals in the periodic table. Everything to the right of the staircase are what are known as our non-metals, and that's going to kind of be what we kind of be what we focus on for the rest of this video here, focusing on breaking down this periodic table into certain chunks and talking about those chunks and how they're kind of arranged on the periodic table, starting with our metals. And again, our metals are on the left-hand side of this periodic table stairs, or the staircase is what I like to call it. Now, some properties of metals specifically are that they are mostly going to be solid at room temperature, except for one very, very specific metal, which is going to be mercury, which again on the periodic table is represented as Hg. That's going to be number 80 on the periodic table. Okay, so if you have your periodic table in front of you, and you want to look at it, okay, Hg is number 80, which is mercury. Okay, that's going to actually be a liquid at room temperature. Metals, for the most part, are shiny and lustrous, right? Lustrous they have luster, they've got shine or sheen to it. They're great conductors of heat and electricity. They're malleable, which is just a basic way of saying they can be hammered into sheets. They are ductile, which means they can very easily be drawn into wires. I know a couple of these terms are ones we've heard in the past, right? But it's always good to kind of touch up on and review them. But yeah, malleable are things that, think about aluminum foil, for example, right? Aluminum foil is made up of the element aluminum, which just so happens to be number 13 on the periodic table, Al. And think about aluminum foil, right? It's a very, very, very thin sheet of aluminum that is essentially been hammered into a sheet, right? It's very malleable aluminum. Ductile, right? Think of copper wiring, for example. Copper wiring is very, very easy to be drawn out into wires, right? That's why it's very commonly utilized as wiring in homes for, electrical wiring and whatnot, right? It's very ductile and can very easily be drawn into wires. Now, if we look at specifically on the periodic table, okay, if we look at the very, very top, I know it's kind of mirrored on my end here, but the very top left of the periodic table, I know it's showing up on the top right, but the top left of the periodic table here is the element hydrogen. Now, although hydrogen is on that side of the periodic table, which is the right or the left-hand side of the staircase, which is with pretty much every metal on the periodic table, it is actually not a metal. It is a non-metal. Okay, it's very important to make that distinction. Okay, so hydrogen is definitely not a metal. It is a non-metal. Now, speaking of non-metals, which is everything on the right-hand side of the periodic table stairs or staircase. Now, the properties of non-metals are pretty much going to be exactly the opposite of what we just read on the metals side, right? So where metals are mostly solids at room temperature, most of these non-metals are going to be gases, or what are known as molecular or network solids, and those are super, super easy to break versus metals that are going to be super, super difficult to break, right? They're poor conductors of heat and electricity. They lack luster. They're not lustrous. They're not shiny at all. They're very, very brittle and easy to break. Okay, so again, a lot of the properties of both metals and non-metals are very conflicting, right? They're exact opposites of each other because, well and truly, the chemical and physical makeup of them are exact opposites as well, right? So it's no wonder that metals and non-metals are exact opposites of each other. Now, metalloids, okay, kind of a funky word, but maybe just from looking and reading the word, you can kind of put together an idea of what a metalloid is. Okay, metalloids, in its most basic way, share properties between metals and non-metals, right? They share properties between metals and non-metals, right? So they've got properties of both, right? They can be shiny, but bad conductors of electricity. They can be very, very dull and lackluster, but very, very good at conducting heat, for example, right? So they can kind of go back and forth based on, what kind of specific element we're talking about is. Now, the location of where they are, they're basically right on the staircase, okay? And there are very, very specific ones that we're talking about here, okay? And I kind of use this phrase here, this sentence, this way to kind of help you memorize them, okay? It says, Bob sits gently as Sabrina talks endlessly about Tom, right? Use this sentence to kind of help you recognize and remember exactly which elements are our metalloids, right? So B, Si, Ge, As, Sb, Te, and At. Those are going to be your 1, 2, 3, 4, 5, 6, 7 different metalloids. Okay, so use this sentence here. Bob sits gently as Sabrina talks endlessly about Tom to kind of help you remember and recognize what our 7 metalloids are going to be. Now, we're going to break down this periodic table into some more specific columns here, or what are known as our groups, right? Starting with the very, very first one on the far left here, which is our group number 1. Group number 1 are what are known as our alkali metals. They are the most reactive metals on the periodic table, right? And essentially, they have just one valence electron on them, and they exist only as compounds in nature. Okay, so for the most part, you're very rarely going to actually see these substances by themselves. So if you pick one off the list here, maybe lithium, for example, right? Lithium is actually very rarely found as elemental lithium, right? Just as a basic element by itself. It's more so found as a compound, as a greater whole to a compound. Alkali earth metals, very similar name, right? Alkali metals in group 1 versus alkali earth metals in group 2. It's the next column over. Group 2 is the next column, and they're the second most reactive group of metals. They've got 2 valence electrons, and they also only exist as compounds in nature. So alkali metals and alkali earth metals, group 1 versus group 2, very similar, right? Very, very similar in most ways. Again, they're both very, very, very reactive metals, and they only exist as compounds in nature as well. Now, on to our next very, very large chunk on the periodic table, which is known as our transition metals. This is going to be basically this really thin piece of the periodic table. I'm going to do my best to point them out, right? This thin piece here, starting from group number 3, which is this group right here, all the way over to group 12 here. So 3 through 12 is this entire middle section here on the periodic table, and that is what we're referencing here. Now, they're also sometimes referred to as our D block elements. That's not really going to be something or a phrase you hear me say often, but plain and simple, they are very, very hard metal solids with very high melting points, right? So they're going to be our traditional metals you think of, right? You're going to think of copper, you're going to think of gold, you're going to think of silver, some other ones, maybe some nickel or cobalt or iron, right? So those are some other transition metals on this list that you can probably think of and know about previously. These transition metals are much, much, much less reactive than our alkali or alkaline earth metals. And they are actually going to form colored solutions when present as an ion. Transitioning over from our halogens, or from our transition metals to our halogens, is going to be group 17, which is all the way over to the right, almost to the very, very last column there. Group number 17, also referred to as our halides. And these are often symbolized by the letter X. These halogens or halides are going to have 7 valence electrons, and they're actually going to be our most reactive nonmetals. So now we've been able to establish both sides of the periodic table, both sides of that staircase, right? The left-hand side has our most reactive metals on the very, very far end in group number 1, and the far right-hand side of the staircase with group 17 has our most reactive nonmetals. Okay, so we got both on both ends here. And these halogens have a very high electronegativity and very high ionization energies as well. Now, on to the noble gases, which I'm sure you guys might have heard about in the past, but they are group 18, which is the furthest group on the right-hand side of the periodic table. They are also called our inert or rare gases, and they've got what are known as 8 valence electrons. These guys are very, very, very unreactive. They're very stable. They're very, very inert. They don't want to react like at all, right? They're very, very unreactive. And they're all gases at STP, right? STP meaning standard temperature and standard pressure, which would be 273 Kelvin and pressure of 1 atm. Now, our diatomic elements, it's going to be one of the last things that we talk about in this chapter here. Diatomic elements kind of came up very briefly back in chapter 3, talking about our particle diagrams. And it's important to recognize that certain elements on the periodic table in nature, they actually exist as 2 atoms of it bonded together, right? It's not just one atom kind of floating out in space with like a lot of the elements in the periodic table. In this specific, acronym, or I'm calling it an acronym, but it's another sentence here to kind of help you memorize it, is have no fear of ice cold beverages, right? You can kind of use this sentence to help you recognize it. Now, remembering that each one of them is going to be Br, I, N, Cl, H, O, and F. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. These are going to be these 7 different diatomic molecules or diatomic elements. Now, ions, okay, I don't really want to spend too much time talking about them because that's going to kind of be saved for one of our chapters coming up in the near future here. But ions are charged particles that result when an atom loses or gains an electron. And more often than not, and I kind of briefly mentioned this in class the other day, more often than not, the charge is going to be represented in the upper right-hand corner of that specific, element or in that specific ion, in what's known as the superscript position. The common charges are written in the upper right-hand corner of the periodic table, on the reference table as well. And here are some examples of them. So the sodium ion is Na+, chloride is going to be Cl-, etc. there is more I want to touch base on with you guys, but we're going to save it for another class. So take care.